Hello and welcome to another GC Basic tutorial for the PIC18FxQ35 chip family. Part 19, assembly, alternative assemblers, try and explain that, and debugging. An interesting area that's we're continually evolving that as we speak in 2026, and we'll keep getting better. So please like this video and subscribe. This is extremely informative. So I've changed the name here because I think in the previous videos it said MPLAB X. Well, do you know what? You don't have to use that anymore. Assembly, alternative assemblers, and debugging. I'll tell you the context, which is quite important. So, GC Basic is, as I've said this, open source compiler for PICs, AVR, and LGTs, about 1,450 now, and it supports this chip. But what I'm going to show you now applies to any PIC that's supported, okay? So it's a common platform. We saw this diagram previously where we sort of explain, or try to explain anyway, where we take source code, it gets pre-processed, it's sucked in with a load of libraries, it gets put into a big long list of code that's been translated, it then gets turned into assembly that is specific for the target architecture. It then pushes out an assembly file and other files, and then it links that up to produce the hex file. And it does that same process for everything. What we can do, we can actually stop the process slightly. It's all automatic, but it's essentially stopping the process. We take the source code, oopsie daisy, and we take into the code translator, into the assembly, and basically GC Basic stops at this point here. It passes out an assembly file that you can read, but it gets passed automatically, and it could get passed into the linker to produce the hex file. We're going to look at it using PIC AS. We can't use MPASM on this particular chip because it's not supported. We could put it into MPLAB, but do you know what? I'm going to sort of leave that there. You can do it into that. It works fine. GPASM, I don't even know what the support level is, and we're not applicable to AVR ASM 2. Okay, so I don't know about this. I don't play with GCASM anymore, and I'm going to show you why that's important. So look, if you're looking at this and it's before 2006, right? You have to do a whole load of hoops to get through to debugging your code. You would have to select a different assembler. You would have to set up a project in MPLAB X, and then you'd import the files produced by GC Basic, and then you'd test compile it, and you could have a look. You could walk the code, and it's a well-trodden step. I've done it thousands of times, but I don't do that anymore because I'm going to show you what we're doing today. So post 2025, the years are different because we've got better capabilities. You're just going to do it in GC Code. You're just going to you're just going to walk the code in GC Code. It's brilliant. So let's go straight into code and we'll have a look. GC Studio, start it up. We've seen all this before, and I'm just going to go straight in, and I'm going to zoom in on my desktop wherever it's gone. And what's it doing down there? And I'm just going to open up the folder. Mine is some funny folder, but yours will be in demonstrations, vendor boards, microchip PICDEM2. Look, you can put these files anywhere. 18F, I don't care. You put them anywhere. All right. Okay. We're in the IDE. On the left, we've got all the files. On the right, we've got the editor. So let's just open up a random file, blink. And essentially, I have got my board attached. Doesn't really matter because we're barely going to use it today. But we're going to look at this. So let's zoom in. Control B to get rid of that side window. We've got a program. It's for the 46Q35. We know that. And it basically turns the LEDs on and off. If you wanted to look at how that works, you create an assembly file. And so what we do is we just make some changes and make sure that your setup is correct. Function key F4 and select Edit Preferences. Then it will take you into the Preferences editor. Let me zoom in for you all. Bring it into Focus. There we go. Look, into the Compiler tab here. And you really need to, I don't know why people use verbose, it doesn't, but I typically use suppress summary, but you might need to see some information anyway. But let me look at the rest of it. You need to check the rest of these, especially show GC basic source in the program and the CDF. We've seen the CDF, but this one is absolutely essential to do what we're going to do. Just going to reset the size here, reset the position so it gets in our view here. And then all I did was just press the reset there, only so we can bring it into view. Okay, we press OK, go back into here. Now, I'm going to compile it, function key F6 rather than 5. I'm not going to program it. Function key F6, push it properly, and it produces a load of output files. So where did they go? Open up the Explorer or press Control B, and there's a folder called O2 blink.build. Looked in here, and it's produced a load of files, many files, but what I'll do it all again because I'm going to clean that folder up. A function key F4, clean the solution. And that's now deleted that folder, and I'm just going to recompile it using function key F6, and it will create an empty folder, a new folder, and here are the essential GC basic files. We'll have a look at that, zoom in. Let me just bring that across. There we go. We've got an assembly file, which we're going to look at, the CDF, we've got the hex file it produced, HTML file, which we've looked at in the past, hexel file, which is the memory map, remember, just the memory map, and the list. And the list is what the compiler did in the linking process. There's a little bit of code at the bottom of this. These are all the constants, by the way. Blink atom. Let's have a look at that. I'm just going to get rid of that list on the side by pressing Control B. And what we've got is the assembly file. It is the assembly file, and we will ask you for this assembly file sometimes. And there's some stuff in here. It says this is where you've got everything installed. This is the source file. This is the ini setting that you used, if you used one. What the preserve mode is, and that means has it got comments in the source, or which assembler it was. Then the output file, let me just say that's the ASM file we're looking at. Float capabilities turned on, and you didn't program it because there's no programmer selected. So we get an awful lot of information about your environment from this one file. It has a list of the configuration that was used. It has a list of the variables, where they lived in memory, in decimal and in hexadecimal, and whether they're shared. Well, was it shared? Shared access means it's faster access. It doesn't mean shared in the sense of shared with anything else, but it lays out, it might not need, it optimizes the memory mapping. And that's all the prep stuff. And then we've got some real code. It says org0, put it at the 0.0 in the memory, go to the bad start program, and then it runs it. And here's the rest of the program. But it's not, you can't walk the code in here. It just shows you the code that was generated from your program. If you want to see what was actually going on in the program, we're going to change the assembler. We're going to walk the code. So this time I'm going to open it up, click. I meant click last time. Function key F4, open the preferences editor. We're going to zoom in on that on the press tool. Zoom in on that, I said. Where is it on the screen? There, over there, look. Compiler. And I'm going to select PIC AS. PIC AS is microchips driver that takes assembly files and produces a hex file. It produces a load more files, which I'll show you. But in there, there's some secrets. So once you've selected that, Press OK. And I'm just going to tidy up the program by pressing function key F4. I'm going to do this a little over here because you're going to see the files. If you look at what GCBASIC produced, 1, 2, 3, 4, 5, 6 files, clean up. We're going to recompile the program in PIC AS. It changes over automatically. You don't have to do anything. And it says it's now compiled it. I'll show you on the screen. It says it's compiled it using PIC AS down here. It's swapped out from the GCBASIC compiler and passed it over, and it's fully integrated. We've done a lot of integration with Microchip to make this all work. But look at the number of files it's produced. Let's have a look in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 files. But in the middle of that, there is some juice. Let's have a look at it. There is the assembly file, ASM, which is our version, and it also produces we produce a .s file. That is a specification by Microchip, not Evan Venn. So I'm going to look at that. Control B, Control J to get rid of the bottom window. Header looks pretty similar, but all of a sudden it gets a lot more information. It's getting information in here to help a tool that I'll show you. Processor, program, memory, etc. Now, the header is slightly different. There's some constants have been defined. The configuration is extremely different. The configuration that is validated, it's validated before we pass it over to PIC AS through this set of configs. Config is completely different, by the way, on PIC AS. The memory is slightly laid out differently, and then the assembly is similar, but it needs a lot more details to make it operate. And that's done automatically, but this file would work in MPLAB. This file is compilable by Microchip's PIC AS driver. But what's the advantage to you? This is the advantage. Back to the GCBASIC source. I'm going to shut that .s. I'll show you. Run, start debugging. At the bottom left-hand corner, it says GCBASIC debug 18F. It's now searching for programmers and all sorts of other things. And it says I've got a simulator built in and a PICKit4 attached, which I have. But I'm going to take the simulator. It now compiles it up exactly as it did previously, but this time it passes it across to the debugger. It brings up a new menu, which I'll show you by zooming in. Here, this area here, right in the middle of the screen, reset, run, step over, step in, step out, restart and stop are debugger commands. Let's look at what's going on. Side window over here has got the variables, watches, nothing set up yet. So let's get the code running. So if I press the down arrow, it takes me into the first line of code, which is exactly where we are. Actually, if I do a reset, it should, oh, there you go, there's the first line of code. Look, BAS start, that's the piece of code, that's the first piece of assembly. It then goes into, always goes into the label BAS program start and calls to a remote call init sys. You didn't add that. It wasn't in our program. All our program did was set the chip and flash some LEDs. So this is put in automatically. And in here, you've got how we set up the configuration for the frequency, how we clear out the ports are set to a digital, etc., etc., clearing out the ports for you, and setting everything to off, and coming back into your program. Our program over here, look, is basically port out and flash some LEDs. Go back to our source code, port out which is why the comments are important. Leave the comments in the code. It says here, select that bank and clear that bit, clear that register. And then it says port B equals 255. Is that in our source? Yes, it is. And we go, and it will set port B to 255. But what's its current value? If I click on it, I can hover over it, or I can just add it into my watch. And I've added the watch on the left here. I press the down key or function F11, and it's going to set all the bits in port B. Now it's going to do a wait. But to be honest, a wait takes a long time in a debugger. So I'm going to actually set a stop point here. So where that red dot is, it will run to that red dot, press continue or function key 5, and it's stopped at that point. I now press F11 or down arrow, reselects the bank. Now you might go, oh, I don't know why that's doing that there. Well, down in the wait, it changed the bank. Okay. And if we look at the debug on the left, you get set to 0. Next command is the wait of 500 milliseconds. I am not going to wait to loop through that lot. And then it stops where I told it to stop at 198, and it goes back to the start. And it goes back to a label, and that label, by the way, is on the bank cell line. This is a full debugger. Now, I would love to have shown you this working into the PICKit4, but it doesn't work because that's a bug inside of, there's a bug that we've reported, and Microchip are working on it, but eventually you'll just be able to, like all the other microcontrollers, you'll be able to just walk that code in real silicon. So you'll be able to select PICKit4 as your debugger, and it will just work. At the moment, it doesn't work. Not my problem, it's someone else's. So what else are we seeing on the left here? We're seeing the CPU registers in here. We've got the registers, and you can look at those in detail. Hardware information. Here's the program memory. You can actually view it if you've got you can view the program memory. RAM, the EEPROM. I wonder what we'll do if, oh, I need to install something, not a hex editor down the bottom. Not, you can do that later yourself, have fun. Unlimited hardware breakpoints. Let's look at the program variables. Something clever, really clever in here that MPLAB and its tools do not do. We can determine if this variable is a word or a byte or a long or a real. It displays it complete. So this is a word variable. You're getting the hexadecimal value, the binary value, and underneath that, these are the 2 bits that made that up, and their addresses. Very clever. Seriously clever, by the way. All right. So in here, these are decremented down. So if we walk the code, F11, puts 254 in there, look, in this variable here, look. And then it puts 1 in the next, and we end up with 1F4, which is the value of 1 into the top byte, and 244 but in decimal down in the bottom, in the low byte, and we get 500. So that says 500 milliseconds. It's been loaded into there, and then it goes down to the, and you can walk that code in delay underscore ms. When it comes back from that routine, there's 0. Look, that value is 0 because it's done its 500 millisecond wait. Look, this is a proper debugger integrated into GC Code. Stop that. Now I've got this code here. I'm just going to get rid of that on the left. I've got some code here. Function key F4, 5, sorry. It will assemble it in PIC AS, and then my PICKit2 is not attached. But I said I had a PICKit4 attached, so let's just change over to that. Here's the list of programmers. Bring it into the view so you can see it. I just need to change the position of the screen there. There we go. I'll drag that down to there for us. And in here, I've got PICKitXtra. And it says I've got an external power supply, which I have. And I'm going to drop that as my first programmer. So it's gone to the top of my list. Press OK. Press OK in the right screen. Go back to the zoom out. Function key F5, or do what you like to get it to program it. Assembles in PIC AS, passes it out, picks up the PICKit4 and programs. It uses DFPs, which are for microchip. Not a problem, they're all pre-installed for you. And then it says it's found it's using one for a QPAC, which is this particular chip. And then it would do its stuff. The LEDs are just flash, so I'm guessing that it's just done it. Yeah, it has. Operation successful. And the LEDs, I'm not showing it on the video, are flashing. So I've used PICKit4. I can use PICKit5, use one of you. I don't care. The essential thing in here is that you can do different things. So let's just look at this from a slightly different way. I am going to take us back just to show you portability here to a 16F886. Does that work? I'm just trying to think whether it's just the port B stuff in this program. There's a port B. There's a port B on an 886. That's fine. And it just GCBASIC knows to patch the source for you. And it's that you could walk that in the debugger, and it's automatically changed everything. And this is code portability. This has changed it from a Q35 to an 866, and you have made no changes in your code. No changes in your code. The low-level assembly, yeah, that's changed. Let's have a look. Here it is, and it says this is totally different. This is all very different. Let's just walk that code. First of all, there's a load of different ports. We got the same bank cell. We got this. Have we got the same delays? Yeah, got the same delays, but it is different assembly. We reassure you, it is really different assembly. If I just walk that back again, the init says it's totally different, and it's totally different. Code portability, but you can see the differences by examining the assembly. Let me put that back. Oh, I tell you what we can do. Function key F4, edit the preferences. I'm going to zoom in so I show you what I'm doing. I am going to turn that over to MPASM, old tool chain. Zoom out, and I can compile it in there. I'm pressing H, make it hex, or function key F6, and it's in that little flash. I'll do it again because it's so fast. Function key F6. It's just compiled that program in MPASM. And it says down here, what? MPASM. You can generate hexadecimal files, assembly files. You choose your poison. It's not down to us. Now, if you've got MPASM selected and you try to debug it, I think it's interesting to see what will happen. In the latest build, latest build of sort of July 2026, it will automatically swap you over to PIC AS because it knows it can't debug anywhere else when we're debugging. Even though you can't debug it in MPASM, but it switched it over to PIC AS for you because that's what you need. You can't debug in the old tools. Okay, you can only debug when using the PIC AS driver. Let me put my setup back to as it was. Edit my preferences. Put that back to GCASM. You can leave it on that because the compiler will automatically select it, but I wanted to show you what it does. Verbose. We haven't looked at verbose. We should look at verbose. Same program, blink, go back to Blink, revert that to our program, chip35, compile up by pressing function key F6, or a lot more information. This is how typically, I think this is the default setup, but I don't have the default. Okay, it says here, look, that's the build number. It's compiling a file, and this is its build directory. Okay, it's all listed out for you. These are all the include files that were sucked in automatically. This is your source program. That's the first one. And then these are all the static libraries that are loaded in. It then loads the source files into RAM memory and then works out all the compiler directives in terms of options, like option explicit. It brings in the DAP file and automatically selects a frequency for you and then calculates, based upon that, the configuration. And that's the first few things it does. It then confirms that I've got a particular chip family, and what the memory is, etc. Then it runs a set of scripts that are all in the libraries, and it starts to sort out what is needed and what is not needed in terms of this particular chip, and it brings in things that are mandated. Some things are mandated, and they're mandated by the libraries. Builds a memory map of all that stuff. Then it does some amazing things. It goes through all the conditional compilation and then creates the variables and constants that are required, and it expands shift operations. It's very busy at this particular point going through your code. Reads tables in. It says here it's using the GCBASIC internal assembler, and then it compiles up all the methods. And if you've got a big program, this would be a long list. We've only got our own program in its sys and a delay, but this can get big. This could get very big. It has a method for allocating RAM to all the variables that have been used. Then it tidies up the code, loads of programmers into program memory. So what it's doing at that point, it's shuffling the memory around, the subroutines around to get them into memory for you. Hence, you can go and look at where that is inside the list file or inside the XHXL file. Then finally, writes out an ASM file, which you can look at. Gives you a summary of that. It says, I have compiled six program lines, and I have used 2 of the 486 subroutines that it came across during the compilation process. Hence it's fast, because it loads them all in and only uses the ones it needs to use. And it says I used 69 words, no RAM, because it's actually shared RAM, and it's got a 64 megahertz internal oscillator. There you go. GCASM, which is GCASM, as I've explained, is very similar to PIC AS, MPASM, GPASM, etc. That's the one that was selected. Builds a symbol table and then generates the machine code. Job done. All that took less than a few seconds. So if I turn off, I'm just going to turn off and suppress all that stuff. I've just selected suppressed mode. Click it to close it. Now I'm going to recompile. I get 2 lines. It says, I did it, I didn't do it. But if I have an error in it, I introduce an error, it still handles it. And then you can click on that and it will take you to the error line. Look, if you want to see what the actual compiling message was, look in the terminal window, and it says here, error has been found, syntax error. It was logged into here. It exited with an error message, fine. So if you want to know what command it ran this command, look. So look, this is the command it actually ran. Between the two, look, here, this is the full command it ran, but you can take this from the C colon for C backslash to the do command, open up a CMD, paste that in, Ooh. You might need some. You need a quote around there. There's a few extra backslashes. Look, that's because that's the way PowerShell works. Didn't find our source file. Why is it not find? Oh, I can see why. There's a backslash there. Look, the backslash is required for PowerShell. I'm not in PowerShell. I don't want to scare you. Look, the same messages. Look, so all we're doing is bringing those messages into here for you. So if I get rid of that little buggy there, save it. Look at that. I'll show you something else before we call this a day. I am going to open up PowerShell. I've opened up a PowerShell. I'm going to move to the directory where this file is installed. So dcolumn, that's where it's installed. Change directory to where that file is. Oh, I'm so sorry. This is, how do I do it in PowerShell? Oh, there you go. So I changed the directory. Let me zoom in and get it a bit bigger for you. Okay, what I'm going to do, I'm going to go back into my source program and put my bug in there. Look, I got a bug. I don't know where it is. I compile it and it comes up with a syntax error. We know that. I'll show you what you can do. Look, syntax error. I'm using a Claude AI agent. And I'm going to take the file name I'm trying to compile. Saying, please resolve the issue in that file name. I've got auto mode turned on. I'll turn it off so it will ask me questions. Manual mode, turned it on. It says it wants to access the file. I go, yeah, well, actually, what it's trying to do is compile the file. I didn't tell it that, by the way. I have not told it how to compile. It's worked it out on its own. It's now going through and says, oh, I've got an error in the line. Do you want me to make an edit to that line? I press yes. If you look behind in the editor, the code has been changed. I want to proceed with a test compilation. Fixed. The file had a stray lone exclamation character between line 28, between optional explicit and the comment block, which caused the syntax error. Removed it, and the file now compiles and assembles successfully. Here's the source file. Change the wait from 500 milliseconds to 50 US. It says, do you want to make this edit? Now you can turn this on automatically, and it's automatically changed the code inside of that file. Do you want to proceed to compile? It's compiled. Both wait times change to 50 microseconds, and the file compiles completely. You can use AI on this source code. It works great. Revert the file. It's now going back, it's thinking. It's asking me to confirm. I want to overwrite things. It's put the file back as it was. It's asking me to figure out whether there's any errors in it. Oh, it was trying to write it back to GitHub. So it actually manually restored it. It didn't pull it back from GitHub, which is quite correct. I didn't give it access to GitHub. Okay, good. Other tools that you can use. Exciting stuff. That was assembling, alternative assemblies and debugging. There's lots you can do. Just a huge subject. I'm going to summarize the video tomorrow. I'll just summarize this all up into one conversation and pull it all together. Goodbye. Enjoy.